Tonight, we're going to explore one of the most hostile and humbling journeys in modern science. A single voyage outward from Mars, past the asteroid belt, the giant planets, and the frozen edge of the solar system. Mars sits about 228 million kilometers from the Sun. Driven without stopping, a car would take roughly 260 years to reach it. And Mars is only the closest neighbor. In the textbooks, it all looks orderly. Clean orbits, neat little planets on tidy white backgrounds. But strip that picture away, and what remains is one of the most hostile, violent, alien places that has ever existed. Radiation that kills in hours. Stars that explode with more power than the sun makes in its whole life. A darkness that grows colder and emptier with every step outward. By the end of tonight, you're going to understand why the space beyond Mars is stranger and more dangerous than any diagram suggests. How each world we pass grows colder, darker, and more violent than the last. And why a universe so indifferent to us still produce something that can look back and understand it. Before we get started, take a second to like and subscribe if you enjoy these videos. It really helps a lot. Now let's begin. Mars is the fourth planet from the Sun, the world humanity has spent decades dreaming about reaching. It is the one taught in every classroom, the rust-colored dot every space agency points toward first, the planet astronauts train for and engineers design landers for, the one name in this whole journey that already feels familiar. On average, it sits 228 million kilometers away. That number alone means very little until you put it in motion. Picture a car, driven non-stop, no fuel stops, no sleep, no meals, nothing but the road. At 100 kilometers an hour, that car would need close to 260 years to arrive. Long enough that it would take generations of drivers, not one, passing the wheel from parent to child to grandchild, before anyone in that family line ever saw the destination. Light makes the same trip far faster than any car ever could. But even light, the fastest thing that exists anywhere in the known universe, still needs about 12.5 minutes to cross that gap. Roughly the length of a short walk to the corner store and back. Except the thing making the trip moves at almost 670 million kilometers an hour. And that is just Mars. The nearest world beyond our own. The one every mission planner treats as close. Everything past it stops fitting on any scale a human mind was built to hold. The picture most people carry from school is tidy. Small circles, evenly spaced. Drifting in calm silence around a bright center. Clean lines, quiet order, the kind of diagram that fits neatly on a single page and asks nothing of the imagination. Strip that picture away, and what is actually out there looks nothing like it. This is one of the most violent, hostile regions that has ever existed. Cold enough, and radiation soaked enough to kill without warning. Filled with objects moving fast enough to erase a spacecraft in an instant. And the first proof of that sits just past Mars. What do you picture happening next? Most people picture empty space, a long quiet stretch of nothing before the next planet finally appears. That is not what is waiting there. The first thing past Mars is chaos. About 2.2 astronomical units from the Sun, the debris begins. An astronomical unit is simply the average distance between Earth and the Sun, about 150 million kilometers. A ruler this whole journey will keep returning to as the distances grow, because ordinary kilometers stop being useful long before this trip is over. This region has a name, the asteroid belt, and decades of movies have trained an entire generation to picture it wrong. Ships weaving frantically between boulders the size of buildings. Rocks tumbling past cockpit windows every few seconds. A corridor you would have to dodge your way through. One wrong move from disaster. How much of that is actually true? How many objects are really out there? And how likely is a spacecraft to hit one on the way through? Wait. In 1972, a spacecraft called Pioneer 10 flew straight through it. Scientists were nervous. Genuinely nervous. Some doubted the spacecraft would come out the other side intact, that something the size of a small boulder would end the mission before it ever reached Jupiter. The belt stood directly in its path, with no way around it, only through. It crossed without a scratch, not a corridor of doom, something closer to an enormous, mostly empty parking lot with a handful of cars scattered loosely across it. The average gap between one rock and the next is so large that spacecraft have crossed the belt again and again in the decades since, and not one has ever collided with debris. But the belt is not simply empty either, and the emptiness should not be mistaken for safety. It still holds an estimated 1.1 to 1.9 million asteroids, larger than a kilometer across. A rock that size hitting Earth would be large enough to end a city. Beyond those sit millions more, smaller stones, pebbles, dust, all of it scattered through an enormous donut-shaped region that circles the sun. Add every one of those objects together, every boulder and pebble and grain of dust, and the total mass comes to less than 4% of the mass of the moon. More emptiness than rock. Spread evenly across that donut-shaped region, the gap between one substantial rock and the next is wide enough that two spacecraft could cross the belt for years and never once see each other. What remains between those gaps is ancient, jagged, tumbling material left over from the birth of the solar system 4.5 billion years ago. Debris that never got the chance to become anything more than debris. It never got that chance because something would not allow it. Jupiter sits beyond the belt, and its gravity reaches back into this region constantly, stirring it the way an invisible hand stirs water in a basin. It pulls objects onto new paths. It flings some inward, toward the planets closer to the sun, and sends others tumbling farther out. It never lets the region settle. Scientists believe there was once enough raw material in this region to build a genuine fifth rocky planet. A real world with its own orbit and its own name. Jupiter kept scattering the pieces before they could ever come together into anything permanent, pulling apart every attempt at a world almost as soon as it began. This was never just failed rubble drifting in the dark. It was a planet that never got permission to exist. But here's where it gets strange. The same gravity that scattered an entire planet's worth of material across a donut-shaped ring is only a preview of what that giant is capable of. Jupiter is the next stop on this outward journey, and it is not simply large. Everything about it is built on a scale that makes the 260-year drive to Mars look almost modest. A scale that turns the asteroid belt behind it into little more than a doorstep. What waits there is not a planet in any ordinary sense of the word. It is a monster, and the most dangerous thing about it cannot even be seen at all. Some things never make it into the diagrams from school. This journey is only getting started, and the first real danger is still just ahead. Cross that debris field, and the thing that scattered it fills the whole view. Jupiter is not simply large. It is a monster. A gas giant so enormous that every other planet in the solar system could be tucked inside it with room left over, orbits and all, and still have space to spare. This is the giant whose gravity spent millions of years stirring the belt behind you, flinging rock inward, scattering rock outward, refusing to let a fifth rocky world ever finish forming. Now the source of that gravity sits directly ahead, filling more and more of the view with every kilometer, a banded orange and cream disk swelling until it blots out everything behind it. The debris field already reduced to a memory of scattered rock far in the distance. The numbers only confirm what the eye already suspects. Jupiter's diameter runs close to 140,000 kilometers. Earth's is roughly 12,700. Divide one by the other and the answer holds almost exactly. 11. Line 11. Earth's up side by side across Jupiter's face, and there would still be room left at the edges. Its mass alone comes to 2.5 times the combined mass of every other planet in the solar system. Not larger than any single world. Larger than all of them added together. Saturn and Neptune and Uranus and Mars and the rest. Every planetary body that exists besides itself, outweighed by this one world alone. A number that size is hard to hold in the mind for long, so the mind does what minds usually do with something too big to picture. It looks for the danger instead, because scale alone rarely kills anything on its own. Numbers like that invite an obvious guess. What could possibly threaten something this size? A collision. Gravity strong enough to crush a ship before it ever got close. The storms swirling across that banded atmosphere, visible even through modest telescopes back on Earth, some of them wide enough to swallow entire planets whole. Surely the thing capable of killing an explorer here is the sheer physical bulk of the planet itself, the crushing scale of it. It is not. The part of Jupiter that would kill an explorer before they ever reached its clouds cannot be seen at all. Earth has something like it on a far smaller scale, a belt of radiation wrapped around the planet, invisible, silent, always there. It was discovered in 1958 by Explorer 1, the first satellite the United States ever put into orbit successfully. Those belts are real. Spacecraft still carry shielding because of them. Extra mass, extra cost, built in specifically to survive a hazard nobody can see with the naked eye. A hazard most people standing on the ground below never have to think about even once. But set against what surrounds Jupiter, Earth's radiation belts are gentle, almost a rounding error next to what comes next. Jupiter's magnetosphere, the bubble of magnetic field and trapped charged particles that surrounds the planet, is the largest structure in the entire solar system. Not the largest planet, not the largest moon, the largest structure of any kind, anywhere out here. If it were somehow visible to the naked eye from Earth, it would appear bigger in the sky than the full moon, and Jupiter sits hundreds of millions of kilometers away, far enough that the planet itself looks like little more than a bright point of light through a backyard telescope. Picture something that distant still managing to outsize the moon overhead, night after night, without anyone on Earth ever noticing it was there. That is the scale of the thing wrapped around Jupiter, an invisible structure larger than any world it protects, stretched across empty space by a magnetic field with no visible edge and no warning sign. Inside that magnetosphere, charged particles, electrons, protons, heavier ions, stripped clean off their atoms, get caught and accelerated to extraordinary velocities. They circle the planet in swirling, invisible bands, layer after layer of them, tightening around Jupiter like a noose that never loosens and never lets go. A human caught inside those bands would not have days to notice something was wrong. Not weeks, hours. That is how long it would take for the exposure to turn lethal, a dose that would normally build up slowly over months or years of ordinary life, delivered instead in a single stretch of hours spent in the wrong place. Less time than one full day, less time than a long flight across an ocean. That is all the invisible bands around Jupiter would need. Here's where it gets strange. NASA sent a spacecraft into that environment anyway, one built specifically to survive it. In 1989, Galileo launched for Jupiter, wrapped in shielding engineered for exactly this kind of punishment, designed by people who understood precisely what waited there and thought they had accounted for it. For a while, the shielding held. Galileo spent nearly 8 years in orbit around the planet, longer than any mission before it had managed. circling Jupiter again and again, passing back through those same lethal bands on every loop, gathering data no telescope back on Earth could ever have collected on its own. But the radiation never stopped working on it. Electronics degraded, slowly, year after year. Instruments began failing, one system at a time, worn down by the same invisible bands that would kill a person in a matter of hours. Shielding built by the best engineers of the era had bought years. It had not bought immunity. Nothing could. By 2003, with its systems failing and its fuel nearly spent, NASA made a deliberate choice. Left uncontrolled, Galileo could eventually have drifted off course and struck one of Jupiter's own moons, carrying microbes from Earth into an environment scientists were determined to keep untouched. So they steered it the other way instead, straight down into Jupiter's own atmosphere, where the crushing pressure and the heat of the descent would tear the spacecraft apart within moments. Its instruments, its cameras, everything it had used to study this world, gone before it ever reached the depths. A death sentence for one of our greatest explorers, chosen on purpose, timed on purpose, all to protect something scientists considered worth protecting even more than the spacecraft itself, more even than 8 years of irreplaceable data. Not the size, not the storms, not the crushing gravity anyone would guess first. An invisible field wrapped around a visible monster, guarding something smaller and quieter than either one. That something is a moon, one of dozens circling this planet, sitting somewhere inside the very radiation that had just spent 8 years grinding a shielded spacecraft down to failure. A world worth a sacrifice like that has to be worth understanding. Whatever it holds down there, it was worth the machine that gave itself up to keep it safe. And it is the next stop on this journey outward. That moon is Europa. And among everyone hunting for life beyond Earth, it might be the single most exciting place in the solar system. Of all the moons circling Jupiter, dozens of them, most of them frozen and unremarkable, this is the one astrobiologists watch the closest. The one name that keeps coming up whenever the conversation turns to where life might actually be hiding. But the reality was different. It sits inside the very radiation that spent 8 years grinding Galileo apart. The same invisible bands that would kill a person in hours. The world worth a sacrifice like that is a world locked under ice, orbiting inside the storm that just finished killing a spacecraft. Picture a lake in the deep of winter, its surface sealed under a hard sheet of ice while the water underneath keeps moving, keeps circulating, alive with its own quiet currents beneath a frozen ceiling nobody standing above would ever suspect. Europa is that idea, stretched across an entire moon and locked in place for who knows how long. A shell of ice wraps the whole surface, smooth in places, cracked and jumbled in others, and beneath it, scientists believe, sits a global ocean. Not a puddle, not a shallow sea, an ocean that may hold more water than every ocean on Earth combined, sealed away under a roof of ice that never melts and never lets the sunlight through. Every drop of it hidden, every current of it unseen. A whole world of water that no human eye has ever looked upon directly, moving in the dark under a shell of ice thick enough to hide it completely. Wherever liquid water exists, life becomes possible. Not certain, possible. That single fact is enough to turn an ice-covered moon, squeezed inside a radiation storm capable of killing a person in hours, into one of the most closely watched targets in the modern search for something alive beyond Earth. Not a rumor, not a guess dressed up as science. A real target, chosen because the physics and the chemistry line up in its favor, sitting there quietly while the radiation that guards it keeps almost everyone else away. Real, actual extraterrestrial life, not the kind imagined in stories, but the kind scientists can actually go looking for, might be swimming somewhere under that ice at this very moment. So how do you even get close enough to look? In October 2024, NASA launched the Europa Clipper, a spacecraft built for one purpose: to reach that ice-locked ocean and find out what it is hiding without ever landing on it. It is one of the most ambitious planetary science missions ever attempted, and the difficulty starts long before it arrives. Designing something that can survive Jupiter's radiation long enough to study Europa up close, gather real data, and send it home across hundreds of millions of kilometers was one of the hardest engineering problems in the history of space exploration. Every circuit, every sensor, every wire had to be shielded against the same bands that finished off Galileo one system at a time. Years of planning went into a spacecraft that will never once set a wheel or a footprint on the ice it was built to study, only fly close enough to look again and again before the radiation eventually catches up to it too. It is not distance alone that has kept this ocean sealed off from us. Europa is not some far world circling a star we will never reach in a human lifetime. It sits inside our own solar system, a relatively short hop past Mars, past the belt, past Jupiter's monstrous bulk, closer than almost anywhere else worth searching for life at all. What keeps it out of reach is the same charged storm that made Jupiter a monster in the first place, still strong enough this far out to threaten anything that lingers near the moon it guards. A possible ocean of life, that close, and reaching it with nothing more than a robot, no crew, no return trip, just a machine built to peek beneath the ice from a distance, has already taken decades of planning and billions of dollars. Not a quick trip, not a cheap one. The nearest ocean that might hold life anywhere in the universe, and it has taken this much just to send something that cannot even touch it, let alone bring back an answer. Now, imagine what it would take to send a person. Not a probe wrapped in shielding and aimed at a careful flyby. A living human being, kept alive, kept breathing, kept warm, for years, inside the same radiation that overwhelms machines built by the best engineers alive. Every safeguard that took a decade to design for a robot would have to be solved again, heavier, more complete, with no room for the kind of gradual failure Galileo was allowed to suffer quietly over 8 years, with nobody's life at stake. A robot can be written off. A person cannot. Every one of those hours that would turn lethal for a human body would still be ticking the entire time anyone stayed close enough to look for an answer. Europa is close enough to dream about, and far enough, guarded well enough, that even reaching it with a robot counted as one of humanity's hardest achievements to date. A world that close, and still that unreachable. The ocean is still down there, sealed under its ice, keeping whatever secret it keeps, patient in a way nothing on the surface has to be. It has been waiting under that frozen roof for longer than humanity has existed, and it will keep waiting long after the Europa Clipper finishes its work and falls silent. Whatever answer it holds, we are still years away from even asking the question properly. And Jupiter, it turns out, is not finished showing what waits at the edge of what a spacecraft or a person can survive. Push past Jupiter's monstrous bulk, and the distances start doing something strange. They keep climbing and climbing until the mind simply stops being able to hold them. Saturn sits an average of about 1.4 billion kilometers from the Sun. Sunlight, the fastest thing that exists, needs roughly an hour and 20 minutes to cross that gap. The same imagined car that took nearly 260 years just to reach Mars, driven at 100 kilometers an hour without a single stop to sleep or refuel, would need about 1,600 years to arrive at Saturn. 1,600 years. Not a typo. A car that left the driveway before the printing press existed would only now be pulling into Saturn's neighborhood. Every stop on this journey outward multiplies the last one, and Saturn is only the second rung on a ladder that keeps getting longer. And yet, when Voyager 1 and Voyager 2 swept past in 1980 and 1981, what came back stopped scientists cold. Not fear this time, wonder. A pale golden giant wrapped in rings so thin relative to their width that, at the right angle, they look like a sheet of paper set spinning edge on, stretching hundreds of thousands of kilometers from edge to edge, and yet vanishing almost to nothing when viewed straight across. Saturn looked less like a planet and more like something an artist had invented. A jewel someone had hung in the dark for no particular reason. No one on the Voyager team had expected the rings to look quite that delicate, that improbable, up close. A glimpse was not enough. Scientists wanted to stay. In July 2004, after a 7-year journey, a spacecraft named Cassini arrived and settled into orbit around Saturn. It was a joint effort, built and flown together by NASA, the European Space Agency, and the Italian Space Agency, 3 space programs pooling their resources for one destination. Cassini stayed for 13 years. It dove through gaps in the rings, circled moon after moon, dipped into the upper atmosphere to sample its chemistry, and sent home a flood of data so large that more than 2,500 scientists around the world have since built entire careers on it. 13 years is longer than most missions manage to survive intact at all, and Cassini spent every one of them getting closer to Saturn's secrets than any spacecraft before it. Patient in a way only a machine with no lifespan to worry about can afford to be. What did all of that closeness reveal? Here is what the data corrected first. From any reasonable distance, the rings look solid. A disk. Something you could reach out and touch as one smooth surface. They are not solid. Not even close. Saturn's rings are made of countless individual particles. Chunks of ice and rock, ranging from grains smaller than a piece of sand, up to boulders several meters across. Billions upon billions of them, all in orbit, all moving at slightly different speeds, depending on their distance from the planet. Constantly colliding, clumping together, breaking apart, and reforming into new shapes, only to be broken apart again a moment later. Seen from a distance, the whole system reads as one calm, continuous ring. Up close, it is closer to a permanent, silent collision. Trillions of tiny impacts happening at once, none of them violent enough to notice, all of them shaping the rings a little differently by the hour. They are not static either. Gravity from Saturn's many moons tugs on them in rhythmic, repeating patterns, a phenomenon called orbital resonance, where a moon and a ring particle pull on each other on the same steady schedule every orbit, the way 2 people on swings settle into the same rhythm without meaning to. That tugging carves waves and ripples through the rings, the way wind carves ripples into sand on a beach. Structure built entirely out of gravity and timing, with no solid material anywhere in the whole formation. Not solid, not permanent in shape, a storm of ice and rock that only looks calm from far away. But the deepest surprise Cassini carried home had nothing to do with what the rings are made of. It had to do with how old they are. Scientists had every reason to assume the rings had been there since Saturn itself formed, a relic hanging on for 4.5 billion years, unchanged, while the planets took shape and life crawled out of oceans on a small world 3 planets closer to the Sun. During Cassini's final orbits, a phase engineers called the Grand Finale, the spacecraft dove again and again through the narrow gap between the planet and its rings, close enough to weigh the material directly. What that data revealed rewrote the assumption completely. The rings are not ancient, they are young, somewhere between 10 million and 100 million years old, against a solar system that has existed for 4.5 billion years. Not a relic, practically newborns. Run that number backward and the consequence lands hard. 100 million years ago, dinosaurs were still walking the Earth. 10 million years ago, they had already been gone for tens of millions of years. Somewhere inside that stretch of time, Saturn's rings simply did not exist, which means there is a real chance that for most of the age of complex life on this planet, the most recognizable feature in the entire solar system was not there to recognize. Just a plain golden dot, bare and ringless, hanging in a sky no one on Earth was yet watching to notice the difference. The rings that fill every textbook illustration of Saturn, the ones that make the planet instantly recognizable to a child who has never looked through a telescope, did not exist for nearly all of the solar system's history, only for this last, thin sliver of it. And here is the part that turns the reveal into something closer to grief. The rings are not only young, they are dying. Saturn's own gravity is slowly pulling the ring material down into the planet. A steady rain of ice falling out of orbit at a rate that could leave the rings completely gone within another 100 million years. Not eventually, in some vague cosmic sense. On a schedule. A window that opened recently by the standards of a 4.5 billion year old solar system, and one that is already closing. Grain by grain, boulder by boulder, with every orbit, Saturn completes. We happen to be alive inside that window. Every photograph of Saturn ever taken, every image a telescope has ever caught of that pale gold giant wrapped in its impossible rings, was captured during a sliver of time that is, cosmically speaking, barely open at all. Whoever looks up at Saturn 100 million years from now may find nothing but a bare planet, the rings long since fallen and folded into the clouds below. The rings belong to no one but this narrow slice of time, and by pure chance, we happen to be standing in it, cameras ready, looking up at exactly the right moment in a story that runs for billions of years on either side of us. Saturn had let us see something almost no one else in the history of the universe would ever get to see. Not a monument, a moment, but the rings, spectacular as they were, turned out to be the least interesting thing the golden giant was hiding. Saturn's rings were not the strangest thing the golden giant had to offer. That distinction belongs to something almost too small to notice. Tucked among the dozens of moons circling it in silence, doing all its most interesting work, where no telescope from Earth could ever have caught it. Its name is Enceladus, only about 500 kilometers across, small enough that a car could drive the length of it in around 5 hours, start to finish, with room to spare. Set beside Saturn itself, or beside Jupiter's monstrous bulk a few sections back, it barely registers as a world at all, more a scrap of ice than a planet-sized body. By every reasonable expectation, that should be the whole story. A dead, frozen ball of rock and ice. Unremarkable. The kind of object a spacecraft photographs once, notes down, and moves past on the way to somewhere more interesting. It is not nothing. A little farther back on this journey, Europa held a hidden ocean sealed beneath armor, thick enough to guard it from Jupiter's radiation, out of reach, teasing at what might be swimming inside. Enceladus does something Europa never does. It hands its ocean over freely, launching pieces of it straight into space, close enough for a passing spacecraft to simply reach out and catch. Cassini turned its instruments toward Enceladus, expecting silence, and found something closer to a heartbeat. The moon turned out to be one of the most geologically active bodies in the entire solar system, a scrap of ice smaller than many countries, somehow more alive than worlds 100 times its size. Not dormant, not quiet, not the dead ice ball anyone had planned for. Restless, changing, venting its own interior into space in real time, on a schedule of its own. At its south pole, deep cracks split the ice open, cracks so distinctive that scientists gave them their own name, tiger stripes. Through those tiger stripes, massive geysers erupt without pause, plumes of water vapor and ice particles blasting hundreds of kilometers up into the dark, far higher than the moon itself is wide. This is not steam drifting off a sun-warmed rock. These are fountains, tall enough and forceful enough to be measured from a spacecraft, still hundreds of kilometers away. Visible proof that something warm and active is working beneath a surface that should have gone cold billions of years ago and simply never got the message. And the moon was not finished surprising anyone. Cassini did not just photograph the plumes from a safe distance, it flew directly through them. Instruments built to catch and measure gas and dust sampled the spray in real time, tasting an alien ocean the way you might catch falling snow on your tongue, and know instantly something about the storm it fell from. What it tasted mattered. Water, the baseline ingredient for everything that follows. Complex organic molecules. The building blocks life is assembled from wherever life exists at all. Molecular hydrogen, the same gas produced on Earth when hot water reacts with rock, a process called hydrothermal activity, chemistry that feeds entire ecosystems in the deep ocean without a single photon of sunlight ever reaching them, and silica nanoparticles, grains that only form when hot water dissolves rock and then cools again, quiet evidence of a heated, active seafloor somewhere beneath all that ice. 4 separate ingredients, pulled from a single plume of ice crystals, on a moon nobody expected to be interesting at all. Water, organics, hydrogen, silica. Every one of them a line in a recipe for something living. Sampled directly, not inferred from a distance. Then came the most recent find, and the one that mattered most. Researchers combing back through Cassini's old data detected phosphorus inside the plumes. Phosphorus is one of 6 elements every known form of life absolutely requires, essential to DNA, essential to the membrane that holds a living cell together. Without it, the chemistry that biology depends on does not work. Not on Earth, not anywhere. For years, scientists suspected phosphorus might be there and simply could not confirm it. One missing piece in an otherwise promising picture. Not a hunch anymore. Not a hopeful estimate. A direct measurement. Sitting in the data. The missing piece finally accounted for. Beneath those tiger stripes sits a global ocean of liquid water, in direct contact with a rocky seafloor, kept from freezing solid by tidal forces, the gravitational squeezing and flexing that Saturn exerts on Enceladus with every single orbit. Squeeze anything hard enough, over and over, and it warms. Friction becomes heat. Heat becomes a liquid sea, hidden inside a moon that has no business being anything but frozen through. An ocean kept alive by nothing more than the pull of the planet it circles. But here's the part that turns curiosity into something closer to hope. The conditions inside that ocean echo something we already know produces life. And it is not a comparison scientists reach for lightly. Deep in Earth's own oceans, at the bottom of total darkness, hydrothermal vents support entire ecosystems under crushing pressure, with no sunlight reaching down that far at all, powered instead by the planet's own internal heat and chemistry. Tube worms, blind shrimp, whole food chains that have never once seen daylight, thriving anyway. If life can take hold there, in conditions that hostile, why should the same recipe fail on a small moon that appears to be running it as well? This is not speculation dressed up to sound exciting. It is peer-reviewed science, published in journals like Nature and Astrobiology, built from direct measurements taken by a spacecraft that engineers on Earth designed, launched, and flew through an alien plume on purpose, years after anyone could have guessed what it would find there. We may have already flown through the ocean spray of a world that harbours life, and simply not known it at the time. Nobody has found a microbe. Nobody has proven that anything swims in that hidden sea. The honest answer is still that we do not know, and it may be years, maybe decades, before anyone can say for certain either way. But for the first time, the ingredients are not missing. They are sitting in the data, one after another. Water, organic molecules, hydrogen, silica, phosphorus, arranged exactly the way a chemist would arrange them if she were building a case for life rather than against it. A tiny, unremarkable-looking moon, orbiting a planet best known for its rings, may be quietly holding the best chance of finding life beyond Earth that we have ever come across. Not because someone theorized it should, because a spacecraft flew through the evidence and brought the readings home. Think about what that means for a moment. 2 worlds so far explored on this journey, an ice-locked moon at Jupiter and a geyser-driven moon at Saturn, and both of them, independently, are pointing toward the same quiet possibility. Water, warmth, and the right chemistry arranged the way life seems to like them arranged, showing up again and again in places nobody expected to find them at all. And whatever warmth is keeping that hidden ocean liquid, this close to the sun's last real light, was borrowed, not permanent. Farther out, past Saturn, that warmth would have nowhere left to come from at all. Leave Saturn behind, and even that borrowed warmth goes with it. By the time you cross into the giant's own orbit, the sun has already thinned to something closer to a bright point of light than a source of heat, only about 100th as strong as it feels standing outside on Earth. Not the difference between night and day, closer to trading full afternoon sun for the last thin light just after sunset, except out here it never gets brighter again. Saturn's average temperature already sits around minus 178 degrees Celsius. Cold enough to freeze most gases solid where they drift. Everything from here on is going to get colder, quieter, and darker than the last stop, and there will be no exceptions to that rule for the rest of the outward journey. And it gets colder. Beyond Saturn is Uranus, the 7th planet, and the first thing worth knowing about it has nothing to do with temperature at all. Every other planet in the solar system spins more or less upright, a top leaning gently as it turns. Uranus does not. It rolls. Tilted about 98 degrees relative to its orbit. It moves around the sun less like a top and more like a bowling ball, rotating almost entirely on its side. Scientists believe something roughly the size of Earth slammed into Uranus billions of years ago and simply knocked it over, and the planet has been rolling through space that way ever since. One violent afternoon in the solar system's youth, still dictating how an entire world turns 4.5 billion years later. Imagine standing on a world where the poles and the equator have effectively traded places, where a year is so long and the tilt so extreme that each pole spends decades facing the sun and decades facing nothing but black. Uranus sits an average of about 2.9 billion kilometers from the sun, more than 12 times farther out than Mars. Sunlight that reaches Mars in about 12.5 minutes needs roughly 2 hours and 40 minutes to reach Uranus at all. Do the arithmetic slowly, and it still surprises. 2 hours and 40 minutes divided by 12.5 minutes comes out to about 13. Light takes 13 times longer to cross the gap to Uranus than it does to reach Mars, and Mars already felt impossibly far back at the start of this journey. Out here, the average temperature drops to around minus 220 degrees Celsius. That makes Uranus the coldest planetary atmosphere anywhere in the solar system, cold enough to freeze nitrogen solid, cold enough that the harshest winter ever recorded on Earth, nearly 90 degrees below zero at a research station in Antarctica, would feel like a mild afternoon by comparison. But here's where it gets strange. Neptune sits even farther out than Uranus, roughly 4.5 billion kilometers from the sun, catching sunlight that takes over 4 hours just to arrive. Do that arithmetic too. 4 hours against 12.5 minutes works out to roughly 19 times the distance sunlight has to cross before it ever touches Mars. By every rule of distance, the planet farther from the sun should be the colder one. Neptune should be the colder of these two worlds. It is not. Uranus is, not slightly colder. Roughly 40 degrees colder, the coldest atmosphere of any planet ever measured, despite sitting closer to whatever heat the sun still has left to give. Scientists still do not fully understand why. Something inside Uranus may simply be failing to radiate its own leftover heat outward the way the other giant planets do, or that internal heat may never have been there to lose in the first place. Nobody knows for certain. What could make one of two near-twin ice giants colder than the other? Is something buried deep inside Uranus quietly failing to do what the other giant planets manage without effort? Or was that internal heat simply never there to begin with, absent from the moment the planet formed, nothing to lose because there was nothing stored away in the first place? Both explanations remain on the table, and neither one has been confirmed. It remains one of the true unsolved mysteries of the outer solar system, a planet that breaks its own neighborhood's rules and offers no explanation for how. Neptune carries a different kind of strangeness, a story about being found before anyone ever laid eyes on it. The eighth and final planet, a deep electric blue world, was not discovered by a telescope sweeping the sky and stumbling across something new. It was discovered by mathematics. Astronomers watching Uranus noticed its orbit was not behaving the way gravity said it should. Something unseen was tugging at it, pulling it slightly off its predicted course, a wobble too small to explain by accident. So scientists sat down with those irregularities and calculated exactly where an unseen planet would have to sit to cause them, working the problem out entirely on paper, with no telescope involved at any point in the reasoning. Then, they pointed a telescope at that precise patch of sky. Neptune was waiting there in 1846, exactly where the numbers said it would be. Discovered on paper before it was ever discovered in a lens. Not a lucky sighting. A prediction confirmed. One of the cleanest triumphs of reasoning in the history of science, achieved without anyone ever having to leave the ground. Neptune keeps the surprises coming once you actually look at it closely. Its winds are the fastest ever recorded anywhere in the solar system, gusting up to 2,500 kilometers an hour, faster than the speed of sound on Earth. Storms the size of entire planets churn through its atmosphere. Among them, one that Voyager 2 photographed in 1989, a storm roughly the size of Earth itself that scientists nicknamed the Great Dark Spot. It later vanished from view and reappeared somewhere else in Neptune's atmosphere entirely, as though the storm had simply packed up and moved on, leaving no trace of where it had been. A weather system the size of a planet, drifting, dissolving, and rebuilding itself in a different patch of sky, on a world so far from the sun it barely qualifies as daylight at all. And that 1989 flyby is still, to this day, the only time any spacecraft has ever visited Neptune. One pass, a matter of hours, nearly 40 years ago. Everything learned since has come from telescopes, staring across billions of kilometers of empty space, including the James Webb Space Telescope, which in 2022 captured new infrared images of Neptune's faint rings, pictures built from light beyond what human eyes can see, details never seen before from any instrument on or near Earth. Think about what that actually means for a moment. This is a civilization that streams live video across the planet, lands rovers on Mars, sequences its own genetic code, and detects gravitational waves rippling through the fabric of space-time itself. And it has spent a few hours, once, at Neptune. Not a returning mission, not a follow-up. One brief pass, decades ago, and silence ever since. The outer solar system remains almost entirely untouched, and there is something quietly humbling in that. A reminder of how much distance still separates what we can imagine from what we have actually reached. How many of the questions still hanging over Uranus and Neptune? The missing heat, the tilted spin, the storms that vanish and reappear somewhere else, are simply waiting for someone to go back and ask again, properly, up close. Two worlds this strange, this cold, and this poorly understood, and both of them were only ever visited in passing. The ice giants mark the edge of the familiar planets, the last worlds anyone bothered giving a number. What comes after them is not a planet at all. Cross that last numbered world, and it is worth turning around just once. From out here, the sun does not look like the thing that warms a beach or lights the summer sky. It looks like a single bright point among countless others. A dot of light adrift in an ocean of darkness, no brighter to the eye than the stars scattered beside it. This is where the neighborhood most people picture when they think of the solar system quietly runs out. 8 planets, a handful of familiar names, and then, on every diagram in every textbook, empty space. What actually lies beyond is not empty. It is a belt, wider and stranger than the one crossed back near Mars, stretching from roughly 30 astronomical units out to about 50, somewhere between 4.5 and 7.5 billion kilometers from a sun that barely qualifies as a sun anymore. Call it the Kuiper Belt. Picture that earlier debris field near Mars, the one that turned out to be mostly empty space with a scattering of rock. Now widen it by a factor of 20. Load it with anywhere from 20 to 200 times the material. That gives some sense of the room this region actually occupies. A donut of frozen debris circling the sun in near total darkness, far larger than anything crossed so far on this journey. That same imagined car from the start of this trip, the one still driving at 100 kilometers an hour without ever stopping, would need something like 5,000 years just to reach the belt's inner edge, and closer to 8,500 years to cross all the way through to its far side. Mars was 260 years away. This is a different order of distance entirely. It is not simply more rubble drifting in the dark. It is closer to a fossil, a frozen archive holding the solar system's oldest secrets. The objects out here, astronomers call them KBOs, are built mostly from frozen volatiles, the plain term for water ice, ammonia, and methane, all lock solid at around minus 220 degrees Celsius, the same brutal cold that already made Uranus the coldest atmosphere in the solar system. These are primordial icebergs, largely unchanged since the solar system itself came together 4.5 billion years ago. They have drifted out here through the entire span of that history, untouched by the volcanic reshaping, the erosion, and the weather that erased most of that early record from the inner planets. Studying one is less like examining an ordinary rock and more like reading a page from a book, written at the very beginning of this neighborhood's history. The ink still legible after 4.5 billion years, because nothing out here was ever warm enough to smudge it. And buried somewhere in the archive, indistinguishable at first from countless other icy points of light, drifting through the same darkness, was an object that would eventually force scientists to rewrite what the word planet even means. In 1930, a 24-year-old astronomer named Clyde Tombaugh sat at the Lowell Observatory in Arizona, comparing photographic plates by hand, night after night, hunting for a single point of light that moves slightly against the fixed stars behind it, the telltale sign of something nearby rather than something impossibly distant. It was slow, exhausting work, one pair of plates at a time, blinking back and forth between them, looking for the smallest shift. The kind of unglamorous, repetitive labour that rarely gets remembered once a discovery becomes famous. He found it. A single point of light, fainter than almost everything else on the plate, patient enough to wait for someone willing to look that carefully. Pluto. For the next 76 years, it carried the title of the solar system's 9th planet, taught in classrooms, printed on posters, memorized by generations of schoolchildren who had no idea how much debate that 9th spot would eventually cause. Then, in 2006, the International Astronomical Union redefined what counts as a planet, adding a requirement that a body must have gravitationally cleared its own orbital neighborhood of other debris. Pluto, sitting among thousands of similar icy objects in the very belt that produced it, had not. It was reclassified as a dwarf planet. The public backlash was immediate, loud, and lasting, and in some corners of the internet, the argument has never fully gone quiet. A definition on paper had reached back through decades of classrooms and quietly rewritten something millions of people had learned as a fixed fact of the universe. Losing that title should have made Pluto smaller in every sense, a demoted afterthought at the edge of the map. Not smaller, more interesting than it had ever been. The proof arrived on a spacecraft called New Horizons, launched in January of 2006. The very same year Pluto's status was stripped away, as if the universe had a sense of irony. It left Earth faster than anything launched before it, close to 58,000 kilometers an hour, fast enough to cross from New York to Los Angeles in about 4 minutes. Even at that speed, reaching Pluto took 9.5 years of travel through empty space, a single spacecraft crossing distances that make the earlier legs of this journey look close by comparison. Almost a decade passed on Earth before it finally reached its target. On July 14, 2015, it arrived. Scientists expected a dead, cratered lump of ice, unchanged for billions of years, nothing left worth finding. What they found instead was almost the opposite. Ice mountains rising 500 meters into a nitrogen sky, close to the height of the Rocky Mountains, standing on a small, frozen world nobody expected to have mountains at all. Vast plains of frozen nitrogen shaped into an unmistakable heart, and named Tombor Regio, after the young man who first spotted this world decades earlier from a darkened room in Arizona. Hints of liquid water that may once have moved somewhere beneath the surface, a thin but genuine atmosphere, mostly nitrogen laced with traces of methane and carbon monoxide, catching sunlight into a faint blue haze when New Horizons turned back and looked at Pluto with the sun behind it. And Pluto was not finished. Whole stretches of its surface carry almost no impact craters at all, and in planetary science that absence means only one thing: young terrain. Something out there, in a world sitting billions of kilometers from any meaningful source of heat, is actively resurfacing itself, smoothing over its own scars faster than the slow rain of impacts over the last few million years could carve them in. Is it heat still leaking from somewhere deep inside? A furnace nobody expected a world this small and this cold to still be running? Or is it the slow churn of nitrogen ice convecting beneath the surface, rising and sinking, the way water stirs in a pot brought almost to a boil? Nobody has settled the question yet. Whatever is driving it has been active recently, not billions of years ago, which means it could easily still be running today, right now, on a frozen world that no spacecraft has visited since, and none is currently scheduled to visit again. What was supposed to be the most boring demotion in the history of astronomy turned out to guard one of its most active, least understood mysteries. Pluto, though, was never the only resident of this frozen archive. It was merely the first one anyone happened to notice. This is not an empty rim at the edge of the map. It is not a scattering of leftover rubble either, waiting patiently for nobody to care. It is a crowd. Astronomers have already catalogued thousands of objects out here, larger than 100 kilometers across, and they suspect hundreds of thousands more are still drifting unseen in the same cold dark that shaped Pluto. Every one of them formed in the same freezing nursery, at the same time, from the same leftover material, and most of them will never be found. Too small, too dark, too far from any light strong enough to reach them and bounce back. A handful, though, are large enough and bright enough to keep turning up in survey after survey. Patient, icy worlds that refuse to stay hidden once telescopes got good enough to look for them properly. Some of them are strange enough to earn names of their own anyway. Eris, found in 2005, turned out to be slightly smaller than Pluto by volume, but heavier by mass. A dense little world whose discovery is the entire reason astronomers were forced to sit down and argue about what a planet even is. For a brief moment after Eris turned up, it looked like the solar system might be about to gain a 10th planet instead of losing its 9th. Haumea spins so fast, once every 3.9 hours, less than a sixth of a single day on Earth, that the spin itself has squeezed and stretched it into the shape of an egg. A planet shaped like something you would find sitting in a carton. Makemake drifts out here too. One more name in a neighborhood that was supposed to be empty, and instead keeps getting more crowded the longer anyone bothers to look. None of these worlds get the attention Pluto gets. All of them are out here anyway, spinning, orbiting, waiting. Then there is Sedna, and Sedna is where this neighborhood stops making sense entirely. A small, pinkish red world on an orbit so stretched that it barely resembles an orbit at all. At its farthest point, Sedna drifts out to roughly 937 astronomical units from the Sun. Take the Kuiper Belt's own outer edge, 50 astronomical units, the boundary that already felt impossibly far only a few minutes ago in this journey, and stretch it out by another 18 times. That is where part of Sedna's year is spent. Nothing about that orbit looks like it belongs to this solar system. Something had to bend it into that shape. Some scientists think a passing star tugged it there billions of years ago. A close call in the deep past that left a permanent scar written into the orbit. Others think something closer to home did the tugging. Something still out there. Something nobody has ever seen. That second idea has a name, and in 2016 it stopped being a rumor among specialists and became a real hypothesis. Two astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, noticed something odd buried in the data. A handful of distant Kuiper Belt objects, Sedna among them, all seem to point their orbits in roughly the same direction, far more tightly clustered than random chance should ever allow. They ran the numbers, tested the alternatives, and kept arriving at the same answer. Something massive, farther out than anything named so far, was quietly shepherding those orbits into line with its own gravity. Not a dwarf planet, not another Pluto, and not another Eris. A real, substantial world, they proposed. Somewhere between 5 and 10 times the mass of Earth, several times heavier than the planet under your own feet, tracing a long, elongated path that never brings it closer than about 300 astronomical units, and may carry it out as far as 800. Sunlight leaves the sun and reaches your eyes in about 8 minutes. It would take more than 40 hours to cross the distance to this planet, if the planet is really there. Colder and darker than anything named so far on this journey, reflecting back only the faintest whisper of sunlight for any instrument on Earth to catch. Nobody has photographed it. Nobody has pointed a telescope at an empty patch of sky and found a new point of light waiting exactly where the math says it should be. The entire case for its existence rests on gravity alone. On the way smaller, visible worlds are being nudged out of place by something nobody has ever directly seen. It is the same method that once found Neptune, a planet's presence inferred from its pull on its neighbours before anyone had looked through a lens and confirmed it. Mathematics reaching a hand into the dark decades before a telescope could follow. Not everyone is convinced the pull is even real. Some astronomers argue the clustering itself may be an illusion, a side effect of surveying certain parts of the sky more thoroughly than others, so that a pattern shows up in the data that was never really there among the actual orbits. It is a fair, uncomfortable question. Look hard enough in one direction, and you will always find something that looks like a pattern. Both camps have spent the years since 2016 pointing survey telescopes at the patches of sky where the missing planet's math says it should be hiding, and both camps are still waiting for a definitive answer. 10 years on, the argument has not been settled either way. Nobody has found this planet. Nobody has ruled it out. That is the honest state of the search right now. Not a discovery and not a dead end. Just an open question sitting in the dark, waiting on better telescopes and more patience than anyone has been able to spend on it so far. Whatever the truth turns out to be, it will not change where this journey has to go next. Because even a planet drifting 800 astronomical units from the Sun, farther out than anything else named in this solar system, is still, by the true scale of what is actually out here, remarkably close to home. Close enough, in fact, that it would still count as a near neighbor once the real boundary of the solar system finally comes into view. That near neighbor, though, is nowhere close to the actual edge. The real boundary of the solar system lies somewhere far beyond even a hidden ninth planet, in a structure so vast, so old, and so poorly understood that astronomers still argue about whether we will ever observe it directly. It has a name: the Oort Cloud. Astronomers have theorized its existence since the 1950s, long before anyone had a way to test it directly. The only evidence comes from long-period comets, icy wanderers that sweep through the inner solar system once every 1,000 years, sometimes once every million, then vanish back into the dark for another cycle. What sends something inward that rarely and pulls it back out again for that long? Their strange comings and goings are the one clue that something out there is doing the sending. The scale of it breaks every number that came before it. This is not a structure measured in a few billion kilometers, or even tens of billions. Current models place it somewhere between 2,000 and 100,000 astronomical units from the Sun. Its outer edge may sit as far as 15 trillion kilometers away. The imagined car that needed 1,600 years just to reach Saturn would need to drive for longer than human beings have existed as a species to cross a fraction of this. Light itself, crossing 300,000 kilometers every single second, needs over a year to travel the whole distance. We have never sent anything there. Not close. The Voyager probes, the fastest objects humanity has ever launched, will not even reach the inner edge of the Oort Cloud for another 300 years. At their current speed, crossing all the way to the outer boundary would take roughly 30,000 years. Longer than recorded human civilization has existed, just to cross one shell of ice, sitting at the edge of our own solar system. Everything we know about what lies out there, we know secondhand, inferred from a handful of comets that happened to wander close enough to notice. Let's walk the numbers the way they were actually built, because scale like this only makes sense one step at a time. One astronomical unit, the distance from the Sun to Earth, equals 150 million kilometers. Neptune orbits at about 30 of those units. The Kuiper Belt, the frozen archive just explored, reaches out to roughly 50. The Oort Cloud is theorized to begin around 2,000 astronomical units out. That is already 40 times farther from the Sun than Neptune sits. And that is only the inner edge. The outer edge is modeled somewhere between 40,000 and 100,000 astronomical units. Take the middle of that range, about 50,000. Multiply 150 million kilometers by 50,000, and the answer comes out to roughly 7.5 trillion kilometers. a 7 followed by 12 zeros. Numbers written out that long stop, meaning anything the moment you try to picture them. So here is what it means measured in light instead. Light can circle the entire Earth 7 times in a single second. 7 full circuits of the planet in less time than it takes to blink. And light still needs roughly 8 months, crossing that same speed the entire way, just to reach the outer edge of the Oort Cloud. Now measure it against something bigger than a planet, bigger than anything named on this journey so far. The nearest star to our own sun, Proxima Centauri, sits about 4.2 light years away. 1 light year runs roughly 9.5 trillion kilometers. Set against that, the outer Oort Cloud, at its farthest theoretical edge, reaches nearly a full light year from the sun. Not a sliver of the way to the next star. A meaningful fraction of it. Almost a quarter of the entire distance. We tend to picture the solar system as a tidy set of orbits, ending somewhere past the last named planet. It is not that. Our solar system does not quietly stop somewhere past Neptune. It thins outward for nearly a light year in every direction, before it finally loses its grip on anything at all. A sphere of gravity so sprawling and so loosely bounded that it bleeds into interstellar space without ever drawing a line. The structure carries the name of the man who first worked it out, Dutch astronomer Jan Oort. In 1950, he published a paper tracing the paths of long-period comets backward through time, trying to find where they had come from. Before Oort, that question had no real answer. Comets simply appeared, crossed the inner solar system, and disappeared again, and nobody could say from where. The comets themselves finally gave him his answer. They did not arrive from one direction, the way objects orbiting in a flat disk like the Kuiper Belt would. They arrived from everywhere, north, south, east, west, scattered across the entire sky with no preferred direction at all. Not a ring, not a disk, a sphere. Oort concluded that something spherical had to surround the whole solar system. A shell of icy bodies in every direction at once, far beyond anything anyone had mapped before. A sky full of comets from every angle turned out to be the fingerprint of a shape. That shell does not sit still. Passing stars occasionally drift close enough to tug at it with their gravity. The slow tide of the entire Milky Way pulls at it too. Rare encounters with giant molecular clouds, vast drifting regions of gas and dust, do the same. None of these disturbances are dramatic in the moment. A distant star sliding by, a faint gravitational tide, barely a nudge by any ordinary measure. But out here, where objects have sat in nearly the same stable orbit for 4.5 billion years, even a nudge is enough to knock a distant icy body loose and send it falling toward the sun. The fall can take millions of years. Only when it finally nears the inner solar system does the ice on its surface begin to vaporize, growing a tail, and only then does it become what we call a comet. Every great comet remembered in human history most likely began its journey out here. Comet Hale-Bopp, which lit up the sky for observers around the world in 1997, is believed to have traveled in from the Oort Cloud, on an orbit that takes roughly 2,500 years to complete. Its last visit to the inner solar system happened when human civilization was only just learning to write. It will not return again until long after everyone watching this has been forgotten. Comet Halley, the most famous of them all, turns out to be something different. Not the Oort Cloud, the much nearer Kuiper Belt, the source most likely behind this short period comet's tight, repeating loop. These comets are not simply ice. They carry the raw chemical material the solar system itself was built from, largely unchanged since the beginning. Some scientists think that material did more than travel, it delivered something. The idea is called cometary delivery, a specific version of the broader hypothesis known as panspermia. It proposes that much of the water filling Earth's oceans, and possibly some of the organic molecules necessary for life, arrived on comets and asteroids during an ancient bombardment roughly 4 billion years ago, a period scientists call the Late Heavy Bombardment. It remains an open question, not a settled one, the same honest kind of unknown this journey has already sat with once before near a much warmer moon. But if it is true, the icy wanderers drifting at the true edge of the solar system may be the reason life exists on Earth at all, and the edge itself is stranger than it sounds. The Oort Cloud has no wall, no border, no line a traveller could cross and know they had left. It simply thins, grain by grain, drifting further and further apart, until there is nothing left to call the sun's own territory. We still do not know exactly how far it truly reaches, or whether any spacecraft we build in our lifetimes will ever confirm it directly. Somewhere out past the last of that ice, the solar system stops belonging to the sun, and something else begins. That something is not nothingness. Most people picture the space between stars as pure vacuum, mile after mile of true, featureless empty, black all the way through, with nothing in it to measure and nothing in it to fear. That picture has always been wrong. Interstellar space is thinly filled, and it has been the entire time. Astronomers call it the interstellar medium, a diffuse mixture of gas and dust drifting between every star in the galaxy, our own sun included. Faint does not mean absent. It has weight. It has chemistry. It has structure that stretches for trillions of kilometers in every direction, quietly there the whole time nobody was looking. The coldest, densest patches inside that medium are called molecular clouds. Vast dark regions built mostly from molecular hydrogen and laced with traces of water, carbon monoxide, ammonia, and more complicated organic compounds. They are some of the coldest places known anywhere in the galaxy, dim enough that ordinary starlight barely leaks through them. Inside that thin fog, researchers have picked out over 300 separate molecules drifting loose in the dark. Amino acids are among them, the building blocks proteins are assembled from. Simple sugar molecules are in there too. The raw ingredients for life are not locked away on distant worlds or hidden under the ice of a moon like the ones already left behind on this journey. They are scattered loose through the galaxy itself, drifting between the stars with nowhere in particular to land, waiting on nothing, going nowhere in any hurry a human clock could measure. Calling any of this a medium still takes some convincing, because the thinness is almost impossible to picture honestly. A typical patch of interstellar space holds roughly 1 atom in every cubic centimeter. The air filling your lungs right now holds about 27 million trillion molecules in that same cubic centimeter. 1 atom. Against 27 million trillion. Spread that single atom across the vast distance between one star and the next though, and the faintness adds up anyway, dragging gently at anything that crosses it, carrying its own quiet trickle of radiation the entire way. Not empty, never empty, thin enough to fool every human intuition about what counts as space, and still, somehow, real. Something else moves through that same thin fog, and this part carries no gentleness at all. Every danger on this journey so far has belonged to a place. Jupiter's radiation belt stayed wrapped around Jupiter. The cold of the ice giants stayed out past Saturn. This one does not stay anywhere. It has no mass. It travels at the speed of light. It slices straight through solid matter without slowing down. Some of it is tearing through your body at this exact moment, through your brain, through every cell in it, and you will never feel a thing. Cosmic rays. They are not beams of light despite the name. They are particles, mostly bare protons, some heavier atomic nuclei, flung to nearly the speed of light, a handful carrying more energy than anything humanity's most powerful particle accelerators have ever managed to produce in a laboratory built for exactly that purpose. They arrive from every direction in the sky at once, with no single point of origin to point a telescope at. Some come from supernovae, the explosive deaths of massive stars. Some come from the crushed remains of pulsars and neutron stars. Some are flung out along the violent jets firing from supermassive black holes at the centers of galaxies far beyond our own. Where the very highest energy cosmic rays actually originate is a question nobody has fully answered yet. One more honest gap in a universe that keeps handing us more questions than answers. Earth blocks most of it before it ever reaches us. The planet's magnetic field bends the weaker particles aside long before they arrive, and the atmosphere absorbs much of what gets past that, shattering each incoming particle into a cascade of smaller ones that fade out long before touching the ground. A little still slips through regardless. It is part of why airline pilots and frequent flyers carry a slightly higher radiation dose over a career than people who stay closer to sea level. And over evolutionary time, it has quietly nudged genetic mutation along. One small, ordinary contributor to the diversity of life on this planet. Working in the background the whole time civilization was busy with other things. Step outside that shield, and the arithmetic turns brutal fast. A one-way trip to Mars with current technology runs roughly 6 to 9 months. About the length of a school year spent entirely in transit. Data gathered by the radiation assessment detector aboard the Curiosity rover, an instrument built specifically to measure this, tracked radiation the whole way to Mars, and again after landing on the surface. What it found suggests a round trip alone would meaningfully raise an astronaut's lifetime cancer risk. Months out, months back. Radiation the entire way, with no magnetic field and no thick atmosphere standing between a human body and the open sky. And Mars is the closest planet there is. It is practically next door on the scale this journey has already covered, and it is already this dangerous. Farther out, it only gets worse. The sun inflates a vast bubble of solar wind around the entire solar system, the heliosphere, and inside that bubble, there is real shelter from the galaxy's most energetic radiation, a kind of borrowed protection the inner planets never have to think about. But the shelter thins with distance from the sun, and past its outer edge there is none of it left at all, nothing but the galaxy's raw, unfiltered radiation pouring in from every side. In August 2012, Voyager 1 crossed that edge, the boundary scientists call the heliopause. Voyager 2 followed in November 2018. Both instruments registered the same thing the instant they crossed it. A sharp jump in cosmic ray intensity, a direct measurement of exactly what any human traveler would face the moment they left the sun's protection behind for good. We do not have the technology to protect a human being through that gauntlet. Not adequately, not close. The shielding required to stop the most energetic particles would be so heavy that lifting it off Earth on any rocket we can currently build is close to impossible. This is not a detail waiting to be engineered around later, some gap that better materials will quietly close in a decade or two. Not a minor obstacle. A wall, and physics has not yet shown us a way past it. Not with better materials alone, not without something genuinely new technologies, possibly new physics altogether. Every world visited so far on this journey has come with a danger you could at least name and locate. A radiation belt around a planet, a stretch of cold, a storm with an edge to it. This is different. This is the background condition of the Gulf itself, present everywhere at once, with no near edge and no far edge, and no technology yet built that solves it. And still, 2 small human-built travelers have already pushed straight through that wall and kept going. carrying a message meant for whoever might someday find it, drifting farther from home with every hour that passes. Neither one was built to survive what it is passing through. Both are still transmitting anyway. How far they have actually come, measured against the true size of the gap between one star and the next, is a humbling story all its own. That story starts with 2 dots of light already beyond the sun's reach, and one number that sounds enormous until it is set beside everything still ahead. Voyager 1 is the father of the pair, and by a wide margin the farthest object any human hand has ever built or launched. Right now, it sits more than 23 billion kilometers from the sun, a number too large to hold in the head until it is translated the way every other number on this journey has been. A radio signal traveling at the speed of light, the fastest anything in the universe can move, needs more than 22 hours to cross that gap and reach the dish antennas still listening for it on Earth. Whisper something to Voyager 1 today, and the answer, if there is one, will not arrive back until tomorrow is nearly over. Voyager 1 is moving away from the sun at roughly 61,000 kilometers an hour, and it has been moving at speeds like that, without pause, without refueling, for nearly half a century. That is not a small feat. What could possibly still be waiting past a reach that large? It is also, as the next few minutes will show, nowhere near as large a feat as it sounds. Voyager 1 left Earth in 1977, and it did not leave empty-handed. Bolted to its side is a golden record, a 12-inch disc of gold-plated copper carrying sounds and images chosen to speak for an entire species, to whoever or whatever might someday find it drifting. Not a warning, a greeting. Greetings recorded in 55 languages open the disc, one after another, a chorus of human voices with nothing in common except the hope that something out there might be listening. Then the sounds of the planet itself, rain falling, surf breaking against a shore, wind moving through trees, thunder rolling somewhere far off, then a mother's first words to a newborn child. The oldest kind of message there is, older than any language recorded on the disc. Then music, Beethoven, Chuck Berry, a Navajo night chant pulled from every corner of human culture and pressed onto a single disc, smaller than a dinner plate. Whoever built that record was not trying to list what humanity had accomplished. They were trying to show what it felt like to be alive here, in case no other proof ever survived to say so. It is the strangest letter ever written, addressed to no one in particular, sent with no return address and no expectation of a reply within any human lifetime. And still it flies, and still it listens, and still, every so often, it answers back. Nearly 50 years after launch, Voyager 1 is still sending data. Faint whispers from the edge of the unknown, caught by enormous dish antennas built and staffed on Earth for exactly that purpose. Every signal that arrives has already spent more than a full day crossing the gap alone. A message from a machine older than most of the people listening for it. Still working. Still calling home from farther out than anything else humanity has ever touched. Nothing about that should still be possible after this long, and yet, every so often, it is. The antennas keep listening anyway, tuned to a whisper that takes more than a day just to arrive. Here is the part that turns the whole gesture humbling. In nearly 50 years of travel, at a speed most of what humanity has ever built cannot match, farther than any human object has ever gone, Voyager 1 has covered less than 1 light day of distance. Wait, not 1 light year, 1 light day. The nearest star beyond our own sun, Proxima Centauri, sits 4.2 light years away, thousands of times farther than Voyager 1 has managed to travel in half a century of uninterrupted flight. Run the arithmetic forward, and the number only gets stranger. At its current speed, Voyager 1 would need roughly 73,000 years to cover that distance, longer than human civilization itself has existed on this planet, longer than agriculture, longer than cities, longer than writing, and it is not even heading there. Proxima Centauri is not in its path. If Voyager 1 were pointed at the nearest star in the sky right now and given all the time in the world, it would still be, for all practical purposes, standing still. Set that number beside everything this journey has already measured. A car at highway speed needed about 260 years just to reach Mars. The same car needed roughly 1,600 years to reach Saturn. Voyager 1 is not a car, it is the fastest thing humanity has ever launched, carrying real fuel, real engineering, 5 decades of uninterrupted flight, and the nearest star still costs it 73,000 years. Every earlier leg of this journey stretched the imagination and asked it to hold a bigger number than the last. This one breaks the pattern outright, because no matter how the number is dressed up, humanity's single farthest reach barely qualifies as leaving the driveway on the scale the stars actually operate on. The stars were never going to care how fast anything we built could fly. That is the lesson tucked inside the golden record and the gold-plated hull carrying it. Our fastest, farthest, most determined machine, launched before most people alive today were born, has barely stepped off the porch. Not close to another star, not on a path toward one, just far enough out to prove that a message can survive the trip, with almost the entire trip still ahead of it, and still transmitting, faintly, decades after anyone reasonably expected it to fall silent. Somewhere past that impossibly small first step lies the true gulf between one star and the next. The gap this journey is about to cross without a spacecraft, using only numbers and imagination, into a darkness filled with something far more violent than distance alone. That violence has a name, and it belongs to the stars themselves. Beyond the asteroids that occasionally worry astronomers, beyond climate and pandemics and war, there is a threat that almost never makes headlines, because it comes from so far outside our own solar system that it barely registers as real. Nobody drafts an emergency plan for it. Nobody watches the sky for it on the evening news. It comes from the deaths of stars so massive they make our sun look like a candle set next to a bonfire. Supernovae. Most stars do not die like that. Our own sun will not. In roughly 5 billion years, it will exhaust its hydrogen and swell into a red giant, ballooning to perhaps 100 times its current width, large enough to engulf Mercury, swallow Venus, and possibly reach Earth itself. It will shed its outer layers into a glowing cloud, a planetary nebula, while its core settles into a dense, quiet ember called a white dwarf. A gentle death. A dignified one. But stars roughly 8 times the sun's mass or greater do not get that ending. They die cataclysmically in one of the most energetic events the universe can produce. And the reason starts with something as ordinary as arithmetic. Inside a massive star, fusion works its way up the periodic table one step at a time. Hydrogen becomes helium, helium becomes carbon, carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, and silicon becomes iron. Iron is where the chain stops. Fusing hydrogen releases energy. Fusing helium releases energy. Fusing iron does not. It costs energy instead of paying it out, and a star has spent its entire life burning fuel to hold itself up against its own gravity. Iron is the one element that refuses to keep the fire going. The core has nothing left to give. So the core collapses. Not slowly. In well under a second, an iron core roughly 1.5 times the mass of the sun, already squeezed into a ball about the size of Earth, gives way completely under its own weight. Earth size to city size. 10,000 kilometers across to 30. In about a quarter of a second. Less time than a single blink. The star's outer layers are still falling inward when they slam into that suddenly rigid core and bounce. The shock wave that follows does not just disturb the star, it tears the entire thing apart, and everything that star ever fused, all that hydrogen and helium and carbon and iron, goes with it. In the first 10 seconds of that explosion, a single dying star releases more energy than the sun will produce across its entire 10 billion year lifetime. Not 10 times more, not 100 times more. Simply more, a comparison that stops meaning much past a certain point. 99% of it leaves as neutrinos, ghostly, nearly massless particles that pass straight through the Earth as if the planet were not there at all. The remaining 1%, still an amount too large to hold in the head, comes out as light, heat, and raw kinetic force. At its brightest, a single dying star can briefly outshine an entire galaxy, radiating more light than 100 billion suns combined. On February 23, 987, that theory became an observation. A star exploded in the Large Magellanic Cloud, a small galaxy neighboring our own, about 168,000 light-years away. Detectors buried deep underground on 3 separate continents registered a burst of 24 neutrinos within seconds of each other, so many at once that they overwhelmed instruments built to catch 1 or 2 a day. Those neutrinos had been traveling for 168,000 years, and they arrived hours before the light did, because they escaped the collapsing star instantly, while the light had to fight its way out through the star's own dense, dying layers. It was the closest supernova observed since Johannes Kepler recorded one in our own galaxy back in 1604, and at that distance, it was never anything but a spectacle. Beautiful, safe, which raises the obvious question: how close would one of these explosions have to be to actually hurt us? Decades of research put the answer at 25 to 50 light years. Closer than that, a core collapse supernova would bathe Earth in a lethal flood of gamma rays, X-rays, and high-energy particles, more than enough to strip away a significant fraction of the ozone layer, the thin shield sitting only 15 to 35 kilometers above our heads that keeps ultraviolet light from reaching the surface. Lose half of it or more, and UV levels would climb to something lethal for most complex life. Food chains would collapse, ecosystems would unravel. It would not be a local disaster, it would be a mass extinction. Here is the part that turns this from a hypothetical into a history. Evidence has been building, drawn not from the sky but from the ocean floor, that a nearby supernova, or a series of them, has already done exactly that. Deep-sea sediment cores contain traces of an isotope called iron-60, a radioactive element forged almost exclusively inside supernovae, and not naturally present on Earth in any real quantity. Any iron-60 left over from the planet's formation would have decayed away long ago. Its half-life is only about 2.6 million years. So when researchers find a layer thick with it, that layer marks the moment supernova material actually arrived and settled onto the seafloor. Multiple teams have now found exactly that, concentrated most strongly around 2 to 3 million years ago, a period that lines up with a wave of climate change and biological turnover some scientists connect directly to a nearby stellar explosion. And there is more. The region of space our entire solar system currently occupies, a pocket of unusually thin interstellar gas called the local bubble, is believed to have been carved out by a string of supernovae going off over the last several million years. We are not reading about this from a safe distance. We are sitting inside the wreckage, which brings the danger closer to home and closer to the present. In the constellation Orion, marking the hunter's right shoulder, sits a red supergiant named Betelgeuse. If it replaced our sun at the center of the solar system, its bloated outer atmosphere would swallow every planet out past Jupiter's orbit. roughly 700 times the sun's own width. It sits around 550 light-years away, more than 10 times farther out than even the closest edge of that 25 to 50 light-year danger zone. Betelgeuse is old in the way massive stars measure age, well into fusing the heavier elements that mark the final chapters of a star's life. The same fusion chain already climbing toward its iron dead end. Astronomers are confident it will explode as a supernova eventually. They are far less confident about when. The honest answer is anywhere between tonight and roughly 100,000 years from now. When it finally goes, it will briefly shine about as bright as a quarter moon, visible even in broad daylight for weeks or months, and sitting safely outside the danger zone. It will not hurt us. It will only be beautiful. In late 2019, Betelgeuse gave the world a preview of just how little warning we might get. Between October 2019 and February 2020, it lost roughly 2/3 of its normal brightness, sliding from around the 7th brightest star in the night sky to somewhere near the 21st. Astronomers named it the Great Dimming, and more than a few of them wondered, quietly and then not so quietly, whether they were watching a countdown begin. The answer was no, not yet. The leading explanation is that Betelgeuse ejected a massive plume of gas from its surface, and as that gas cooled into dust, it simply blocked some of the star's own light from reaching us. Essentially a stellar sneeze, on a scale nothing in our own solar system could ever produce. The dust dispersed. Betelgeuse brightened back to something close to normal. But the episode was a reminder, and not a comforting one. Massive stars in their final stretch are not stable. They are unpredictable, restless furnaces that can shift dramatically over months, not centuries, and one day, without warning, one close enough to see with the naked eye is going to go all the way. Everything from the iron dead end, the collapsing core, the neutrinos, the ozone, the sediment in the seafloor, is what happens when a massive star finally runs out of road. The explosion itself, violent enough to briefly outshine a galaxy, is not even the strangest part of what a dying star leaves behind. What survives at the center of all that wreckage turns out to be even more extreme. A star with many times the mass of the sun tore itself apart in a matter of seconds, briefly outshining a galaxy, and then it was gone. But the explosion is not the last chapter. When the crushed remnant of the core stops collapsing, what is left behind is not fire, and it is not light. It is a neutron star, and it may be the single strangest kind of object the universe has ever assembled. Everything about it defies the intuition built by a normal life on a normal planet. Picture the mass of the sun, or close to twice it, squeezed into a sphere only about 20 kilometers across. You could drive across the entire thing in about 12 minutes, if the surface did not vaporize you first. A city-sized ball holding more matter than a star. That is where the strangeness starts, not where it ends. Consider what that density actually means. A single teaspoon of neutron star material would weigh roughly 10 million tons here on Earth, more than every car ever manufactured in a single country, compressed into a spoon. Nothing on the periodic table behaves like this. It is not a solid in any sense our chemistry recognizes. It is matter crushed until protons and electrons are forced together into neutrons, packed edge to edge, with almost no empty space left between them. The surface gravity is about 200 billion times stronger than the gravity holding you in your chair right now. Drop something from a height of 1 meter, barely higher than a kitchen counter, and it would slam into the surface at roughly 2 million kilometers an hour. The impact would release energy on the scale of a nuclear bomb, not from orbit, not from a great fall, from 1 meter, and these collapsed stars spin. Picture a figure skater pulling her arms in, spinning faster as she draws in tighter. A dying star's core does the same thing on a far more violent scale, shrinking from something wider than the sun down to the width of a city while keeping all of its original spin. The result is rotation on a scale nothing else in nature reaches. Some, called millisecond pulsars, complete hundreds of full rotations every second. The fastest one ever measured, PSR J1748-2446 AD, spins 716 times a second. Its surface moves at roughly a quarter of the speed of light. As they spin, many of these stars fire beams of radiation out from their magnetic poles, radio waves, X-rays, sometimes gamma rays. The beams do not point straight out toward us on purpose. They simply happen to be locked to the star's own axis, and the star's own spin carries them around and around like the rotating lamp inside a lighthouse. The beams sweep through space the way a lighthouse beam sweeps across dark water. When one of those beams happens to cross Earth, our instruments catch it as a steady pulse, on, then off, then on again, with timing more precise than an atomic clock. That regularity is exactly why we call them pulsars. In 1967, a graduate student named Jocelyn Bell Burnell picked up a signal like that for the first time. It was so mechanically regular that she and her supervisor, Anthony Hewish, briefly nicknamed the source LGM1, Little Green Men. Not a serious theory. More a half joke about a signal that sounded too perfect to be natural. It was not aliens. It was a star, spinning hundreds of times faster than anything should be able to spin, sweeping a beam of radio light past Earth on a schedule better than anything humans had built. Not artificial, not even close, and somehow more extraordinary for being real. Some neutron stars are not finished getting stranger. In a smaller fraction of them, the magnetic field grows so powerful, trillions of times stronger than anything a human laboratory can generate, that they earn a separate name entirely, magnetars. Come within roughly 1,000 kilometers of one, something that will never actually happen to any of us, and the field alone would be enough to end your life before you understood what was happening. Not from heat, not from radiation in the way we normally mean it, from the field itself reaching into every cell in your body and tearing apart the electron bonds that hold your own molecules together. About 30 magnetars are known in our galaxy right now, and each one ranks among the most violent single objects that exist anywhere. In April 2020, one of them announced itself in a new way. A magnetar called SGR 1938 plus 2154, sitting roughly 30,000 light-years from Earth, close enough to still be inside our own galaxy, let out a burst of radio waves that multiple telescopes on the ground caught at the exact same moment. What made the discovery enormous was the shape of the signal. It matched something astronomers had been chasing for over a decade, without ever finding a confirmed source, a fast radio burst, a pulse of radio energy so concentrated it can briefly outshine an entire galaxy, and it lasts only milliseconds. For years, these bursts had arrived from other galaxies, billions of light years away, with no way to trace where they came from or what produced them. This one, close enough and clear enough to pin down, finally tied at least some fast radio bursts directly to magnetars. Here's the part that keeps radio astronomers checking their instruments twice. Some fast radio bursts repeat, not once, not twice. The most studied repeating source, called FRB 121102, has fired hundreds of times since it was first caught. Some bursts arriving in tight clusters, some falling into patterns nobody has fully explained. A single flash from a dying star's remnant is strange enough on its own. A signal that keeps coming back, sometimes with a rhythm underneath it, is the kind of thing that makes a careful scientist's mind go somewhere it usually is not allowed to go. A small minority of researchers have quietly asked the obvious, uncomfortable question: could some of these repeating bursts be artificial, sent on purpose by something rather than produced by accident? The honest answer, based on everything the evidence shows so far, is no. The overwhelming consensus is that fast radio bursts are entirely natural. Almost certainly the flares of magnetars doing exactly what magnetars do under stress nobody fully understands yet. What causes some of them to repeat in patterns and others to fire once and go silent forever is still an open question. One more honest unknown in a universe that has offered up plenty of them already. But that a leftover corpse of a dead star, spinning alone in the dark with no audience and no intention, can produce something so strange that trained scientists have to pause and rule out intelligence before moving on, says something about this universe. It does not need our help to be strange. A star's core collapses into a city and somehow keeps spinning. That spin becomes a beam, and the beam becomes a pulse, and once in a great while the pulse becomes a scream loud enough to cross 30,000 light years and still register on Earth. None of it was designed. None of it was sent with a purpose in mind. It happens on its own, over and over, in the ordinary, indifferent business of a violent galaxy. The same galaxy that also happens to be building instruments sensitive enough to catch a whisper from a dead star on the far side of it. And somewhere past every remnant, every beam, every burst, something else is waiting at the center of it all. Something that would make even a neutron star look small by comparison. Follow that thread far enough, and it leads somewhere specific. Every neutron star, every magnetar, every burst of radio light this journey has passed, all of it orbits one place. Not a planet, not a star, a single dark point at the center of everything, and reaching it means admitting something first. You are not standing still to read this. You never have been. Right now, without feeling a thing, you are moving in two directions at once. Earth carries you around the sun at roughly 17,000 kilometers an hour, several times faster than a bullet leaving a rifle, and the sun itself, dragging Earth and every planet in this journey along with it, orbits the center of the Milky Way at roughly 828,000 kilometers an hour. That works out to about 230 kilometers every single second, far enough to cross a mid-sized country before you finish reading this sentence. One full lap of that orbit, a galactic year, takes the solar system somewhere between 225 and 250 million years. The last time Earth sat in this exact spot in its galactic orbit, dinosaurs had not yet evolved. Trilobites were only beginning to vanish from the oceans. Every war, every empire, every book ever written happened during a single sliver of one lap. We are passengers on a star, and the star has been circling the same dark center since long before anything alive could notice, and will keep circling it long after we are gone. That center has a name, Sagittarius A star, roughly 26,000 light years from Earth. Measure that against everything already crossed. The gap that took Voyager an imagined 73,000 years just to begin closing, the 4.2 light years to the nearest star, is a rounding error next to this. The galactic center sits more than 6,000 times farther out than that. And at the middle of it waits a supermassive black hole holding the mass of about 4 million suns, all of it packed into a region smaller than the distance from our own sun to the orbit of Mercury. Here is what that actually means. A black hole is a place where gravity has become so extreme that nothing escapes it. Not matter, not light, not even a radio signal. The boundary is called the event horizon, and it is not a surface you could touch. It is the exact distance at which the speed needed to escape exceeds the speed of light itself. Cross it, and you are gone. Not delayed, not damaged. Gone as completely as if you had never existed at all. Sagittarius. A star's event horizon has a radius of roughly 12 million kilometers, more than 17 times the radius of the Sun itself, and against the scale of the galaxy, it is still nothing more than a pinprick. For decades, nobody could see it. Astronomers could only infer it was there by watching what orbited it. A team led by Reinhard Genzel and Andrea Ghez spent more than 25 years tracking individual stars near the galactic center, with infrared telescopes built to see through the dust that blocks ordinary light. What they found should not have been possible. Stars moving at up to 30 million kilometers an hour, roughly 3% of the speed of light, locked into tight, fast orbits around a point where nothing visible existed. The only explanation was a black hole of about 4 million solar masses. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for that work. Then, in May 2022, the Event Horizon Telescope collaboration did something that sounded almost impossible. A global network of radio telescopes, linked together to act as a single instrument the size of the Earth, sifted through petabytes of raw data to produce the first direct image of Sagittarius A star. Not a simulation. Not an artist's rendering. A real photograph, blurry and glowing, a ring of superheated gas wrapped around a dark central shadow, hard-won and years in the making. It is one of the most extraordinary images science has ever produced. Is it dangerous? At 26,000 light-years, its direct pull on us is nothing. We orbit it exactly as every other star does, gently, stably, the way Earth orbits the Sun. It is not coming for us, but the neighborhood around it is not peaceful. Star density near the center runs thousands of times higher than out here, so collisions, near misses, and gravitational slingshots happen constantly. Supernovae go off more often. Radiation runs hotter. It is, by every measure, one of the most crowded and violent patches of real estate in the entire galaxy, and we are fortunate to be watching it from 26,000 light-years away, rather than living inside it. When gas, or the shredded remains of a star, spiral toward the black hole, they do not fall in cleanly. They form a swirling disk, heated to millions of degrees, and some of that energy gets funneled into jets. Narrow beams of plasma blasted from the poles at nearly the speed of light, stretching for thousands of light years. In 2010, the Fermi Gamma Ray Space Telescope found the evidence of just how violent it can get. Two enormous structures called the Fermi bubbles extend roughly 25,000 light-years above and below the galactic plane, a quarter of the galaxy's entire width, glowing in gamma rays. The leading explanation is that Sagittarius A star itself inflated them, somewhere between 2 and 8 million years ago, during a period of intense feeding. 2 million years ago is recent enough that early human ancestors were already walking the African savanna. We live in a galaxy with a supermassive black hole that has, in geological terms, only just gone quiet. And here is where the whole journey turns. Every world this trip has passed was hostile in its own specific way. Radiation that kills in hours. Cold that no shelter fixes. Stars that die by tearing themselves apart. A galactic center that spent the last few million years blasting bubbles of gas larger than most galaxies. None of it was built with us in mind. None of it cares whether we exist at all. And yet, on one small, water-covered world, orbiting an unremarkable star in an unremarkable arm of this galaxy, something happened that, as far as anyone has ever found, has happened nowhere else in the observable universe. Life appeared. And after billions of years of nothing more dramatic than chemistry slowly rearranging itself, that life learned to look up. It learned to measure the distance to stars it will never visit. It detected gravitational waves from black holes merging a billion light years away. It flew a spacecraft through the ocean spray of a moon around Saturn. It photographed the shadow of a black hole 26,000 light years from home. Consider what you are actually made of: carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus. Every one of those atoms was forged inside a star that died before the sun ever existed. The iron carrying oxygen through your blood right now was made in a supernova. The calcium in your bones was cooked inside a red giant. The oxygen filling your lungs was breathed out by a star that ended, scattered across space, and eventually gathered by gravity into you. Not metaphorically, literally. You are not a small, fragile thing standing outside the universe, looking up at something alien. You are the cosmos, arranged into a shape that can look back at itself. Every question about the stars, every ounce of wonder any of us has ever felt looking up, is the universe wondering about itself through you. Carl Sagan put it more simply than anyone else has managed since. We are a way for the cosmos to know itself. The space beyond Mars really is worse than you think. Radiation that kills in hours. A vacuum with no bottom. Cold with no ceiling. Violence on a scale nothing on Earth prepares you for. That much is true, and none of it softens for wishing it would. But it is also ours. It is the universe we happen to live inside, and the fact that we can understand even a fraction of it, that we can look at a smear of noisy data and say, correctly, that is the shadow of a black hole 4 million times heavier than our sun, is not a small thing. It might be the largest thing anyone has ever done. Feeling small in front of something that vast is not a defeat. It is the beginning of understanding what you actually are. Mars, the asteroid belt, Jupiter's radiation, Saturn's dying rings, the ocean under Enceladus, the deepening cold of the ice giants, the long dark past the heliopause, the stars that end their lives in fire, the crushed remnants left spinning in the wreckage, all of it led here to a dark point 26,000 light years away, and to the atoms sitting in your own chest that came from the same place. The universe is old, violent, indifferent, and almost incomprehensibly large, and somewhere inside all of that, still paying attention, still looking up, still asking, what is out there? Are we?